We will see in this example, kinetic energy recovery, the difference in flow, with and without, kinetic energy recovery, in a fluid flow system with a drop. Here we have the entrance, at 0 altitude, and the exit at an altitude of minus 0.46 meters. We use MechAFlux Pro 3D to simulate and calculate the flow in this small system with a reduction in diameter, generating an acceleration of the fluid at the outlet. We calculate the flow that will come out of this system with a gravity water intake. We set up a gravity water intake and obtain the flow rate of the system. We obtain a flow rate of 76 cubic meters per hour. Here we see the gravity water intake with a reservoir outlet pressure drop. We show the pressures with a color scale. We see the atmospheric pressure, inlet and outlet, and here, the evolution of the pressures. In this particle test, we see that the fluid picks up speed in this cone. And at the system outlet, the fluid retains a speed and significant kinetic energy. So the energy balance, head loss and output kinetic energy generates a flow rate given to us here, 76.5 cubic meters per hour. We are now going to simply insert an enlargement at the output of the system with a slight angle, so as not to cause too many pressure drops. We know that for diffusers, 12 degrees is the best compromise. So we apply 12 degrees. We insert this diverging cone downstream of the duct. This diffuser will therefore slow down the fluid and modify the distribution of pressures on the path of the fluid. We are going to restore a fluid at the outlet with less kinetic energy than that which we had without the diffuser cone. We calculate the flow with this same variation in altitude, and we see that our flow has increased to 129 cubic meters per hour. The kinetic energy, which was previously wasted, has been saved by the system. The overall balance shows less energy loss, and the flow rate balancing the losses is greater. This phenomenon is exploited in hydroelectric power generation systems. The manufacturer places a turbine here, in the area offering the greatest pressure delta. The system has a better performance with this diffuser cone, also called aspirator, because of the depression it generates at its entrance. We see that our fluid is returned to the outside with less kinetic energy. The angle of the diffuser cone is important, because a cone angle that is too open will generate a pressure drop, which will be negative in the overall balance, and reduce the overall efficiency of the system.